All right, this is section 10.2, probability, and we talked a lot about different terms, different vocab words in our last section, outcomes and events, so what we're going to do today is we're going to talk about the probability of those events, and the probability of an event is a number that measures the likelihood that an event will occur. Now, probabilities can range from anywhere from 0, which is the lowest probability, and 1, which is the highest probability. You can't have a probability that's lower than 0. That would be negative. And you can't have a higher probability that's higher than 1. And the reason for that is because when we look down here at this chart, 1 as a percent is 100%, and you can't have anything be higher. You can't have any probability be higher than 100%, because if it's a 100% probability, it's certain. And if it's a 0% probability, it's impossible. Now, if it's from anything from 0 to 50%, we say is in this range here, this is called unlikely. So if it's 1%, 25%, 49%, those are all percents that are unlikely. It's more likely to not happen than it would be to happen. And then, of course, if it's 50% or 1/2 or 0.5, we would say it's equally likely to happen or not happen. And you'll just hear me refer to this as equally likely. Sometimes I'll say 50-50, right, where it's 50%. But you'll hear me more often than not say equally likely. That just means 50% or 1/2. And then anything in this range from 51% up to 99% is in the likely category. So any fraction that falls in there, 0.6, 0.75, 89%, those are all likely probabilities. And then, of course, 1 or 100% is certain. So probabilities can be written as fractions, decimals, or percents, but we normally see them written as fractions or percents. This first example wants us to describe the likelihood of an event, so we're just going to use one of these options, one of these words they've given us, either impossible, unlikely, equally likely, likely, or certain. And for example A, it says there's an 80% chance of thunderstorms tomorrow. Well, that means it's likely going to storm. So that 80% would fall in this category. Somewhere right in here would be 80%. And then for example B, it says the probability that you land a jump on a snowboard is 1/2. Well, 1/2 would be 50%, so we would say that is equally likely. That would be right there, smack dab in the middle, equally likely. Example C says there's a 100% chance that the temperature will be less than 120 degrees Fahrenheit tomorrow. Well, thankfully that's certain, right? We don't want the temperature to be that high, so 100% would be certain is what we would call that. I'm just using that chart that we had in the last example. And then example D, there's a 20% chance of snow flurries tomorrow. Even though our weather's been very crazy here in April, this would still be unlikely. Unlikely. So 20% is low. It's less than 50%. It's not impossible. It's not 0%, but it is unlikely. Okay, so when all possible outcomes are equally likely, the probability of an event is the ratio of all of the number of favorable outcomes to the number of possible outcomes. Now, we talked a little bit about this yesterday, but probability, again, normally written as a fraction, so that's why it says a ratio right there, because that's a fraction. If I was wanting to roll a die, and I know there's 6 numbers on a 6-sided die, and I was wanting the probability of rolling a 2. Well, there's 1 2 out of 6 numbers. So the favorable outcome there is me rolling the 2, and there's only one of them. That's why I put a 1 on top, not 2. It's not the number I want to roll. I just put how many numbers I have, or how many different 2s I have, and I just have 1. And then I put on the bottom the number of possible outcomes. There's 6 different numbers. So that's how we find probability. And when we talk about probability of an event, in this case, the probability of, like I said, of rolling a 2, we put whatever we're trying to do, whatever the event is, in parentheses. So it looks like this. The probability, capital P, probability of the event is the number of favorable outcomes over the number of possible outcomes. All right, here we go with that number cube. It says you roll the number cube. Number cube, again, is just a six-sided die. Find the probability of each event. So rolling an odd number. So the way I would write this, I would say the probability of me getting an odd number, so I put odd in parentheses, is I'm going to write it as a fraction, and I need to know how many odd numbers there are. So here's all my possible outcomes. And of those 6 possible outcomes, I have 3 of them that are odd. I also have 3 that are even. So my probability is going to be 3 out of 6. Again, the number of favorable outcomes, the ones I've underlined, over the number of total outcomes. And then, of course, 3 6 will reduce to 1/2. There's an equally likely chance that I roll an odd number as an even number. For example B, rolling a number greater than 4. So I'm going to use a greater than symbol and just put 4 in there. Of the great numbers that are greater than 4, I'm talking about 5 and 6. Not 4, because 4 is not greater than 4. It's equal. So I have 2 out of 6 numbers that are greater than 4, and that's going to reduce to 1/3. For example, C, it says a number greater than 2. So greater than 2. The probability of me getting a number greater than 2, well, 3, 4, 5, and 6 are all numbers greater than 2. So I have 4 out of 6 chance of that happening. And 4, 6 reduces to 2/3. And then part D here, it says rolling a 7. Well, there aren't any 7s that I can roll. So the probability of me rolling a 7, let's write it like that, would be 0 out of 6, which of course is 0. And remember, that's our lowest probability. This would be impossible, is what we would call that. Impossible. You can't roll a 7 when you're only rolling one number cube. So if you're writing your answer as a fraction, make sure you reduce all of your fractions. You can also choose to write it as a percent if the problem allows you to do that. It may say write it as a fraction. It may say write it as a percent. It may say write it as both, but make sure all your fractions are reduced. So let's look at some different things we can do with probability. This problem says the probability that you randomly draw a short straw from a group of 40 is 3/20. Well, how many short straws are there? Well, I'm going to use that probability of 3/20. That 3/20 means there's 3 short straws for every 20. That doesn't mean I have 20. I have 40. It tells me that. So if I have 3 short straws out of 20, then how many short straws would I have out of the 40 that I know I have from the problem? And I can just set up a proportion. Now, this is a super easy one to solve. I don't even have to use cross products if I don't want to, because I noticed that 2 times 2 is 40, and so 3 times 2 would just be 6. So x equals 6. So in this stack, there's 6 short straws. Whoops, can't spell. Straws. So we can use the probability to actually find out how many of those favorable outcomes are there. There's 6 short straws. Here's a similar question in case you need another example. It says this time there's 50 straws, not short straws, but total straws, 50 total. And the probability of me getting a short straw is 9/25. So if there's a 9 out of 25 chance that I'll get a short straw, then, or if there's 9 short straws out of 25, maybe it's a better way to say that, then how many short straws would there be out of 50? And just like the last problem, you're going to see me times by 2. And we find out x has to be 18 short straws. Now, if you don't see that you can use mental math like that, go ahead and use cross products. There's no problem with that. 25x, 9 times 50 is 450. And then you just divide by 25 and you'll get 18. So you can still solve the proportion, or if it's as easy as these proportions are, just use mental math. But what happens when they don't give you a fraction? What if they give you a percent as the probability? Well, there's actually 2 ways I could do this one. First of all, you can turn that percent into a fraction. You can say 2 out of 100. That's what percents are out of, right? Percents mean out of 100. So if 2 out of 100, it says there's a 2% chance of being born with red hair. So if 2 out of every 100 people are born with red hair, then how many would that make out of 650? Right? And so I can cross multiply this one. This one's not one I probably want to use mental math for. So 100x, and then 2 times 650 is 1300. and then I can divide by 100, and that's going to give me 13 people with red hair out of 650. Or there's another way. If I know 2% of the population is being born, right, there's 2% chance, I could just write this. 2%, we know of means multiply, right? So 2% of 650 people, which is 0.02, if you write that as a decimal. And if you do 0.02 times 650, you'll still get 13 people being born with red hair. So we actually have a couple different options there. I actually think this option here to the right is the easiest one to use because I didn't have to solve a proportion. I just had to type in 0.02 times 650. Let's look at some homework problems. Number 19 is the first one I want to look at. And this is an interesting one. It says a dodecahedron. So a dodecagon is a polygon that has 12 sides. A dodecahedron is a three-dimensional polygon. It actually has 12 sides. So just think of it as a 12-sided die. And yes, they do exist. It has 12 sides numbered 1 through 12. Find the probability and describe the likelihood of each event. So A says rolling a number less than 9. So I don't know if you need to do this or not, but I'm going to go ahead and just, again, list out all the possible outcomes. Maybe you're a little bit more visual. I'm very visual, so I like writing these out. And then I'm just going to think, okay, rolling a number less than 9. Well, how many of the numbers are less than 9? Well, 8, 7, 6, 5, 4, 3, 2, 1. You get the picture, right? So 8 out of 12 numbers are less than 9. Now, of course, 8/12 reduces to 2/3, and you can see that option right here. And if it's 2/3 likely, that's more than 50%, but less than 100%. So we're going to say it's likely that we get one of those numbers. Now, for part B, it says rolling a multiple of 3. Well, remember multiples of 3. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. And 3 times 4 is 12. So there's 4 out of the 12 numbers that are multiples of 3, and that's going to reduce to 1/3. You can see that option right here. And because that's less than 50 but more than impossible, we're going to just say this one's unlikely. And then for the last one here, rolling a number that's greater than 6. Well, that means 7, 8, 9, 10, 11, and 12. 1, 2, 3, 4, 5, 6. 6 of the numbers are greater than 6. So 6 out of 12, which it reduces to 1/2, or 50%, would be this option right here. And that's going to mean it's equally likely, or 50-50. Now, number 20 may be one of my favorite problems of the entire school year. I love Punnett Squares. I liked taking biology in high school. I took biology when I was in college as well. And I don't know if you guys have worked with Punnett Squares before. Maybe you have in science. But a Punnett Square is used to determine the likelihood of a baby's genes or an offspring. It doesn't have to be a human baby. It could be any animal or plant. And so what they do is they take the genes from the mother and father, place them on the sides of the table, and then they fill in the boxes appropriately. So this one, it says, is giving us the option for a boy or a girl. So a boy is represented by XY, and a girl is represented by XX. Okay, so it's the Y chromosome that actually determines whether a baby is going to be a boy or not a boy. And so because girls have X chromosomes, you can see mother's genes as XX on top of the Punnett square. And because boys are XY, you can see the father's genes in blue are XY. So we just have to fill this chart in. So mom's going to give the X chromosome. In fact, she's always going to give the X chromosome because that's the only chromosome she has. And then dad could give an X chromosome. So I'm just filling in with that then. Or he could give a Y chromosome. And so if you're XX, you're a boy, or sorry, you're a girl. And so you have a 2/4 chance of being a girl. And if you're XY, you're a boy, and you have a 2/4 chance of being born a boy. And of course, both these fractions reduce to 1/2, which is why half of the population, or in fact, if you look at the world population, it's incredibly how accurate this gets. Maybe not so much when you look at the population of just our classroom, but if you look at the school population or the state of Indiana or the United States population, or even better, the world's population, it's so close to 50% that you can hardly tell a difference. There are even if there's a couple 100,000 more girls than boys, in this grand scheme of billions of people, that's really not that much. And so the probability of being born a boy or girl, it's 50-50. It's equally likely. So for number 21, I think I went ahead and answered that already, this question. Obviously, we filled in the table. We filled in the table last time. And it says, explain why the probability of two parents having a boy or having a girl is equally likely. Well, the probability of having a boy, we said, is 1/2, and the probability of having a girl is also 1/2, so that would be equally likely. Now, this Punnett square in number 22 is not giving us boy or girl. It's going to give us whether the hair is curly or straight. And so they tell us in the instructions up here that if you have a capital C gene, that you have curly hair. And if you have the S gene, lowercase s, you have straight hair. So anytime they use a capital letter, that recognizes a dominant gene. So that gene will take place whether there's a little s or not, doesn't matter. You'll see that gene. And if you use a lowercase letter, that's called a recessive gene. I'm not sure if I'm spelling that correctly. It doesn't even look like good handwriting. But recessive genes are always hidden genes. So anytime there's a capital gene, you can see the mother and father both have this capital gene here. That means both of them have curly hair. Yes, they're called what's called a carrier. They carry that straight-haired gene, but they're not going to show it because the capital C is the dominant gene. They're going to show the curly hair. And so if two people get married and have kids, mother and father, both have curly hair, but they're both carriers, here are the possible outcomes. You can have a CC, capital C, capital C. You can have a CS, capital C, lowercase s. You can have a capital C, S again, or you can have an SS, both lowercase. Now, when you're typing these in, make sure you use capital letters. I forgot to mention that for the first problem we did, but make sure you're using capital letters when you're doing this, and then use a lowercase letter for the S. And so those are the four options. So this baby is obviously going to have curly hair. This baby will have curly hair, but it'll look just like mom and dad. It'll be a carrier. And this baby will have straight hair because there isn't a curly gene to cover up the recessive gene, so it would actually have curly hair. It says the probability of the gene combination capital C is 1 out of 4, so it has a probability of 1/4. And for part B, any gene combination that includes a C results in curly hair. That's because it's dominant. We just talked about that. When all outcomes are equally likely, what is the probability of a child having curly hair? Well, we have 1, 2, 3 of these kids having curly hair. So we have a 3 out of 4 chance they have curly hair, and then obviously that leaves us with a 1/4 chance that they would have straight hair. So there's a 1/4 chance that they're completely dominant. There's a 2/4 chance that they're going to be carriers, and then there's a 1/4 chance that they'll be straight hair. But altogether, that does make a 3/4 chance that they're going to have curly hair, because whether they're dominant or just a carrier, they're going to have curly hair unless they have the two lowercase s genes.